We are talking about more organized counting. This is the second lesson in our unit on permutations. In this lesson, what we're going to do is add some restrictions, which will restrict the total possible number of outcomes that we can have in permutation questions. So restrictions, what they do is that they'll limit either the number of times that we can use an object, or they'll put certain conditions on where objects can be used or when objects can be used. And it can make counting problems a little bit more tricky because you have to pay attention to very specific things. Our first example is a very typical permutation question in that it starts out very easy with no restrictions, and then we start adding restrictions on top of the very simple scenario. So here in question A, how many different 3-scoop ice cream cones can be made from vanilla, chocolate, and strawberry ice cream? Well, what we want to do is we want to say, first of all, there's no restrictions in this case. Repetition of flavors is allowed. It doesn't say anything about it. That's what we're going to assume. So we have our stages, or our places where we can put an ice cream cone, or an ice cream scoop, excuse me. We have a place for scoop 1, scoop 2, and scoop 3. And so how many choices do we have for scoop 1? Well, we have 3 flavors, so we have 3 choices. And we would have the same for scoop 2 and the same for scoop 3, giving us a total of 27 different flavor combinations for this ice cream. In part B, of course, how many different cones can be made if each flavor can be used only once? So here we introduce a very basic restriction, and that's that, okay, now we're not allowed to use repetition. So here's our placeholders for scoop 1, scoop 2, and scoop 3. For choice 1, for scoop 1, we'd of course have 3 choices. For scoop 2, though, we now don't have 3 choices anymore. We've already used 1 flavor, so now we're down to 2 choices. And then for the last scoop, we don't have any choice at all. So if we can use each flavor only once, there's only 6 different cones that we can get. Here's our notation. We want to include the proper notation for part A and for part B. So here, the number of total 3-scoop cones is 27, and here the number of cones without repetition is 6. So in part C, this is the final restriction in this question. How many cones can be made where at least 2 scoops have the same flavor? So at least 2 scoops means, okay, so what's all right? 2 scoops the same is good, and 3 scoops the same is good. But what we don't want is we don't want a cone where all of them are unique. And so what we're going to do here is we're going to say, okay, well, how can we accomplish this? And we realize now with this kind of a restriction, we have to count very carefully. So we'll set up 2 cases. Case number 1 is the case when we have 2 scoops the same. And case number 2 is the case where we have 3 scoops the same. Okay? Within case 1, let's examine that first. We have 2 scoops the same. We have to establish many cases within this case. The first case, let's say the top and the middle are the same and the bottom is different, right? That's one possible arrangement. We could have, though, the top and the bottom being the same and the middle being different. And if you follow the pattern, we could also have the top being different, the middle and the bottom being the same. So how many options then do we have for each of these? Well, in the first case, we've got 3 options for that top scoop because it can be anything that we want. But because the middle has to be the same, we don't have a choice anymore. So we're limited to 1 flavor only. And then we would have 2 options for the bottom. Here in the next one, where the top and the bottom are the same but the middle is different, we'd have 3 options for the top, but we'd have no options for the bottom. It has to be the same as the top, so there's only 1 possibility. And then there would be 2 possibilities for the middle. And in a very similar way, we have an interesting pattern for the third. So how many does this give us? Well, we'd have 6, and because these are mutually exclusive, you can't have top and bottom being the same when the top and the middle are the same. You know, these are all mutually exclusive. They can't happen at the same time. We'd have a total of 18 different cones where 2 scoops are the same. Case number 2 then becomes very straightforward. How many different cones can you have where all 3 are the same? Well, we could have all chocolate, we could have all vanilla, or we could have all strawberry. So we've got three permutations there. So the total number of cones that we could have where at least 2 are the same, is 21 different cones. In part C above, that was a lot of work. We had to consider a lot of cases, and we had to complete our calculations. Sometimes it's easier, though, to count the total number of outcomes that don't meet the conditions and then subtract that away from the total number of outcomes without restrictions. So if we look at that above, let's take a look at what we would have had. The total number of cones without restrictions minus the number of cones where everything is unique equals the number of cones where at least 2 are the same. And we can see the pattern here. N total cones minus n cones without repetition equals the number of cones where greater than or equal to 2 of the scoops are the same. And 27 minus 6 is, of course, 21. And this is the indirect method. We'll see it over and over again. So let's do another example to get used to it. If we go back to 6C, and this was one that we tried to tell you to do on your own, we can use an indirect method. So the question was, using the digits from 0 to 9, how many 3-digit numbers are possible that contain at least one 5? So if you had solved that question correctly, you would have gone through and you would have said, okay, here's the cases. 1 5, and where can they be? 2 5s, and where can they be? 3 5s, and where can they be? Well, in this case, let's take the total number of permutations of 3-digit numbers of the numbers 0 to 9, and we're going to subtract off the numbers without a 5. Because our condition is how many contain at least 1. Well, what we don't want, we want anything but just no 5. So we'll subtract that option off, and then we'll get the number of permutations with 1, 2, or 3 5s. So here's all, and this was kind of the part A in that question. 900 3-digit numbers, and we subtract off the case with no 5, which was 648. And what we see is that 900 minus 648 was equal to 252. And that was the answer, and we got it in a much simpler way. So the number with 1, 2, or 3 5s was 252. As we get into more advanced counting problems, we're going to have more and more restrictions. So here's a big one. How many 6-digit even numbers over 300,000 can be formed using the digits 0 to 5 without repetition? So there's lots of restrictions in here. Let's take a look at what they are. First of all, an even number tells us that out of the digits that we have, it must end in a 0, 2, or 4, because we're only working with the digits 0 to 5. Over 300,000 tells us that the first digit has to be a 3, has to be a 4, or has to be a 5. Without 0 to 5 means that we only have 0, 1, 2, 3, 4, and 5 to work with, so there's only 6 numbers to work with. And so let's take a look at how we're going to do this. Let's set up 3 cases. One case is that it starts with a 3. One case is that it starts with a 4. And one case is that it starts with a 5. These are, of course, mutually exclusive, so we're going to add the result using the additive counting principle at the end. So what we can say is that if 1 starts with a 3, we don't have a choice there. It's locked into position. The last number, it has to be even. So if it starts with a 3, how many choices do we have for the last number? Well, it could be a 0, it could be a 2, or it could be a 4. So we have 3 options. If there's no repetition then, we've used a 3 up front, we've used one of those 0, 2, or 4 at last, then we would have 4 times 3 times 2 times 1 options for all the middle numbers, because we've subtracted off and we can't use repetition. So the total number of 6-digit even numbers starting with the number 3 is 72. Let's do the same thing for 4. For 4, however, we only have one option for the first case. For the first place, it's got to be a 4. But for the last number, it's an even number. We can't use the 4 again. We've already used it in the first place. So now we don't have 3 options for the last number. We've only got 2 options for the last number. And the 4 times 3 times 2 times 1 is exactly the same as before, and it's 48. Very similar situation with the 5. But now we can use 0, 2, or 4 in the last place, and so we get 72. And when we add up these cases, the total number of 6-digit even numbers over 300,000 that can be formed using the digits 0 to 5 without repetition is 192.